Here we are again with first class physics with Ms. First. That's me. Now I know I'm going to blow your mind with the technologically advanced equipment that I'm using here today. We are going to be adding vectors in 2 dimensions. That's what we're going to be doing today, and we're going to be doing this using an example. Word problem. Oh no, I'm freaking out. I'm going to teach you how to deal with word problems as we go along. But the first thing we do is just read it one sentence at a time. Don't panic. If you find yourself panicking, you need to take time to relax, because the fact of the matter is your brain shuts down as soon as you start to panic. So you can't panic. Take the time to relax. You can either breathe or maybe shake it off, do a little dance, whatever you have to do, you do it. But you've got to be calm and relaxed, otherwise your brain is going to shut down and the time you're taking is worthless. So let's just read one sentence, and if the one sentence stresses us out, we're just going to read part of a sentence. So let's see here. George the, oh, that looks like eat. George the cat walks 2 miles east and then walks 20 degrees west of north. Oh, what? I don't understand. Freak out, freak out. All right. You don't want to freak out. So now we're just going to read half the sentence. George the cat. I get it. There's a cat. And you're also going to be blown away with my amazing artistic ability. I truly am an amazing artist. All right. I understand George the cat. Got it. Okay. He walks 2 miles east. All right. I think I got that. Let's see. Left, west. So east is right. So here's where he starts. And he walks 2 miles east. All right. So I took care of this part here. Now, then he walks 20 degrees west of north. What does that mean? Well, let me show you how to break this down. West of north. So what I do first, and this is the doing it oftentimes Ms. First does it the dummy way, and by that I mean I like to break it down and make it as simple as humanly possible. Now, we're not going north. We're going west of north. So first I draw a dotted line north. We're not going north. We're going west of north. West, when we draw it, is typically left as long as north is up. Okay, I guess I should have put a compass up here. We have north is going upward on our map. So here we're not going north. We're going 20 degrees west of north. So this here is 20 degrees. All right, we're 20 degrees from north. And let's keep on reading. How far is he from where he started? Well, what we're going to do here is we're going to put a little dot here. That's where the cat ends. This is where the cat starts. And what we're looking for, our big fat question mark, is we basically want to know what is this displacement vector from where he starts to where he ends. So that, my dears, is our question mark. And we can even call it the variable d. We can have it our vector d for displacement. So we're basically taking these 2 vectors and we want to add them together to find out what the replacement vector is. So I just showed you step 1 of solving any physics problem at all, and that's drawing a sketch. Now all of those scary words, you don't have to look at them anymore. We have a nice little sketch that just replaced all of those big, scary, freaky words. And there it is. Now the physics starts. Oh boy, now we panic. Oh, I did forget to label this right here. 1 mile, right there. Boom. Okay, now the panic sets in. No, don't panic, relax. So we want to find out what this vector is. Well, let's see. I have this vector here is 2 miles. This vector here is 1 mile. So he must have walked a total of 3 miles, right? Womp, womp, womp. No, that's not right. Well, I don't understand why this is not right, because I know if the cat walked 2 miles and then he walked another 1 mile, I know that he walked 3 miles. So it works in this case. We can just add the magnitudes of those vectors, but it doesn't work in this case. It's really weird. I also know that if he walked 2 miles this way and then backtracked and walked 1 mile this way, I know I can just add those vectors because it's 2 miles plus a negative 1 mile. Oh, I'm going off my screen. Plus a negative 1 mile, and that's going to end up being 1 mile. I know he ends up only 1 mile. So why does it work for these two and not for this case? Well, the reason is we can only add vectors that are parallel. We can only add vectors that are parallel to each other. And the problem is these guys, these two black vectors, are not parallel. So let's take a look at this. First of all, I'm going to randomly name this vector, vector A. Okay, I'm going to call this vector A. And I'm going to call this vector here vector B. It's getting kind of messy here. I'm going to call this vector vector B. Now, what I ultimately know is I know that my displacement vector, my total displacement vector, is equal to vector A plus vector B, the two legs of his journey. But I can't just add the magnitudes of that guy and get 3 because these vectors are not parallel. So what I need to do is any vector that's an angled vector, any vector that's at an angle, I call these rebel vectors. And the reason why I call them rebel vectors is because they're not nice and horizontal. They are not nice and vertical. They are at an angle. Now, before we get more confused with my little crazy drawing, let me just draw a little axis here, because I know this is at an angle, but I just want to remind us that this direction here is nice and horizontal. Maybe I should be nice and make it horizontal on your screen. And with my amazing technological magic, I fix it. Okay, so now we see that this is horizontal, left to right. Straight up and down is vertical. But we have this rebel vector here, this crazy rebel vector that is not horizontal and not vertical. So we can't just add it. We just can't. It doesn't work that way. So we're trying to figure out what this nice purple vector is equal to. But we're just going to get rid of that just for a second so we have some room to work. Well, what we do to rebel vectors is we need to break them down. We need to break those rebels down. We need to break rebel vectors down into horizontal, which we call X, components, and vertical components. We absolutely need to break them down before we can add them together. So let's take a look at breaking these vectors down. Well, so vector A has an X component and it has a Y component. Because vector A is completely horizontal, it is all X. Every little bit of the distance of 2 miles is only in that X direction. So the magnitude for vector X is 2 miles. There is absolutely no part of 2 miles that goes up. There's no part of 2 miles that goes down. So the Y component of the 2 miles is 0. There's no part of that. There's absolutely, positively no part of that A vector that goes up or down. So we are going to say the X component for vector A is 2 miles, and the Y component of vector A is 0 miles. That was easy enough. Now, here's that vector that's an issue. It's an angled vector. So I'm just going to blow this vector up a little bit. We're just going to blow it up just a little bit. I'm going to take the same exact vector, but I'm just going to make it a little bigger right here just so that it's easy for us to see. And we said that this is 1 mile, and we said that it is 20 degrees from north. In our case, that's 20 degrees from vertical. If you notice, every diagonal line is really a hypotenuse to a right triangle. So we are going to use some old tricks of geometry. Say, you know what? This angled line, if I was a cat and I walked from here to here, I would end up in the same exact place if I was that cat and I walked straight up this amount and straight over this amount. So every single angled vector can be magically turned into 2 components. Now the question is, what is the x component and the y component of this angled vector here? And again, we named that vector b. What is the x and the y component of this vector? Well, using good old, and now we're going back into our memories from either late in geometry or early in trigonometry, we learned all about this little tool called Sohcahtoa. And if we use this little tool, Sohcahtoa, we are going to be able to figure out this. Now, here's our review. We're going to review Sohcahtoa. The first thing we need to do is identify our sides. Well, I know that this guy is a hypotenuse. Angled vectors always are the hypotenuse. This little guy is our attached. Okay, I know everyone else in the world calls it adjacent. I like to think of it as attached because this side is attached to the angle that we know. You see that? This side and this side, the hypotenuse, are what make up that angle. So he's literally, this side is attached to the angle. This side is completely opposite. He's not attached, he's opposite. So now I'm going to say, okay, what side do I know? I know H. I know H. I know he's 1 mile. Which side am I looking for? I don't know. If I wanted to find my x component, I need to be looking for my opposite side. And that would be O. So it's just like Santa Claus. Ho, ho, ho. So let's find O and H in our Sohcahtoa. Let's see. There's an O, but no H. There's an H, but no O. Look at that. So, a needle pulling thread. We need to use our SO equation, which is sine theta equals opposite over hypotenuse. And now I'm going to plug in what I know. I know my angle is 20. I know my opposite side. Well, that's what I'm looking for. I'm looking for that opposite side, and that opposite side is the x component of my vector. So that's sine 20 equals opposite, which is bx over, and the side that I know is my hypotenuse, and that's 1 mile. I multiply 1 on both sides. 1 times sine 20 equals bx. The magic of calculator tells me that bx is approximately equal to 0.342. There, I now know my x component of that vector. Now I'm going to do the exact same thing for y. All right, now I know my hypotenuse still. And now I want to know my y components. We called this the y component of our b vector. So that is the adjacent attached side, and ha! I got it. Let's see. So, well, it has H, but it doesn't have A. Ka is the only one with both H and A in the equation, and the ka is the equation cosine theta equals adjacent over hypotenuse. I'm going to plug in what I know. My adjacent side is my y component of b. My hypotenuse is 1. So now we have all of the components that we need. And remember, we can add vectors that are parallel. The only other thing that we have to do, and I'm classic at forgetting this, classic. I made a boo-boo and a lot of you out there were like, Miss First, what did you do? So let's go back and backtrack. I took this angled vector, which is the same vector as right here, and we broke it down and we randomly called this vector B. And we broke this down into its y component and its x component. So basically we're saying these two vectors are exactly the same as this angled vector. So the beauty of it is when you have an angled vector, which is pretty useless, especially when we get into projectile motion, because in projectile motion you're going to have equations you can use for the x direction and equations for the y, but there are no equations that you can use for vectors at an angle. So you're going to absolutely have to replace every angled vector with the y and x components, or the x and the y components. Well, I made a boo-boo here because vectors have direction. So if we look at our system here, we're saying positive x goes to the right and positive y goes up. Well, here I have an x component going to the left, so that means it must be negative. And my y component goes up, which means it must be positive. So do not ever, like Miss First did, forget that you have to add those directions in right then and there. So now that we have our components, we are able to figure out the components of our vector D. Remember way back when, about 5 years ago, okay, about 15 minutes ago, that's what we were looking for. We wanted to understand what is this vector right here, and we randomly called this vector D. We wanted to understand what that was. Well, we now can say, okay, well, the x component of vector D is equal to the x component of A plus the x component of B, and the y component of vector D is equal to the y components of A and B. So when I plug in the new values I just learned, recalling Sohcahtoa, I know my x component of A is 2. My x component of B is negative 0.342. My my y component of A was 0. My y component of B was 0.940. So and through the magic of the phenomenal technology that Miss First is using, when I simplify this, I have an x component of 1.658 miles and a y component of 0.940 miles. Well, that's all fine and dandy, but I want to know the resulting vector D. And look at that nice straight line. Okay, it's supposed to be straight. So right now I have figured out the x component of D and the y component of D. Oh, that's all fine and dandy, but I want to know this big blue guy. Well, let's take a look at this. Let's erase all this stuff. This is all kind of pointless to us, pointless at this juncture because we've already figured out those components. So this is what we're saying. The x component is here. The y component is here. And think back, doodly-doop, diddly-doop, way back in your history. If you know two sides of a right triangle, how do you figure out the side of the third? Remember, it's all in changing your representation. So yeah, you have these numbers, but you always want to back it up with a sketch because now you see, well, that's hunky-dory. In order to figure out the magnitude of this vector, I can use my good old friend, say it, Pythagorean Theorem. So I just take the square root of the sum of the x component squared plus the y component squared. And when I do that, I'm going to fast forward here. I see that the magnitude, in this case the length of this hypotenuse, this angled rebel vector, is 1.906 miles. Now, of course, we're not taking into account significant figures at this juncture, but it's a vector. Vectors need magnitude and direction. Well, the direction of this guy can be explained with this angle. And this angle here can be determined using, that's right, our good old friend Sohcahtoa. So let's take a look at Sohcahtoa. And yes, there are lots and lots of steps, and it's overwhelming. And Miss First, you've been drolling on and on for 20 minutes now. But listen, as long as we break things into one itty-bitty step at a time, you can do it. So again, we know a side, we know an angle we can use, we know two sides, and we want to know an angle. So anytime there's a side and an angle involved, we know we can use our tool Sohcahtoa. So I'm going to go ahead and use, let's use this guy here, okay? One thing you want to remember is you really don't want to round during your calculations, because then you will end up with round off error, and we don't want that to happen. So especially if you work for NASA, okay? We've got to be very, very careful here. So using Sohcahtoa, again, the first thing we do using Sohcahtoa is identify our sides. Well, this side is attached. Okay, you math people, we can call it adjacent. Everybody else think of it as attached. It's much easier. But this side is attached. We're going to put a big A on it for this side here. This side over here is another one we know. That's opposite. So the key formula, let's see, there's an O here but no A. There's an A here but no O. OA right there. That is the... Is it acronym? Do you call it acronym? I'm not sure. Tangent theta is equal to opposite over adjacent. It's the theta that we're looking for. Our opposite side is 0.940. Our adjacent side, our attached side is 1.658. And we're going to, in order to release this theta, the only way to release this theta is to do the opposite. The opposite of taking the tangent of an angle is to take the inverse tangent. So we do that to both sides. When we plug that into our handy dandy calculator, we're going to get 29.55 degrees. So our angle is approximately 30 degrees here. Okay. And now we know our vector. Our vector, the magnitude of it is 1.9 miles, comma, 30 degrees. Now, when we don't specify, 30 degrees always means up from the positive x-axis. But if you remember, the original problem had north, east, west, all of that. So really, the kitty cat, I believe it was a kitty cat, it was a long time ago. The kitty cat is 30 degrees north of east. Because the cat's not walking east, he's walking 30 degrees north of east. That's really messy, but remember, step by step. So let's just overview what we did. We wanted to find out what our vector was. So we broke down all rebel vectors. So you break down all rebel vectors. And again, this is adding 2D vectors. The first thing we need to do is break down all rebels, all those rebels without a cause. Then we add x and y components to find, my ADHD is really coming out here. You see my brain is like skipping ahead and I'm missing letters and all kinds of fun stuff. Add x and y components. You're going to add those x and y components to find your resultant x and y components. And then the last thing we did was we added our x and y components vectorially. Oh boy, that's a long word, and I could have just made that up. I have absolutely no idea. Using Pythagorean Theorem to find the magnitude, and we use Sohcahtoa to find the angle. And that's all there was to it. It really was easy as soon as we started to break it down into teeny tiny little steps.